Hello and welcome to Into the Terminal. Today we're going to be talking about system memory and swap and virtual memory and not virtual memory. So,
all,
hey,
all kinds of important and super interesting things, or at least they're super interesting when they need to be.
right, exactly. When you get that page.
Yeah,
Uh,
yeah,
so, Nate, shall we jump into the terminal and um, take a look at the critical path?
absolutely. So we've covered some tools, right, in lots of our troubleshooting episodes and whatnot, and this is going to feel a lot like some of those episodes because we're going to go over some tools about how you can look at memory usage on your system and kind of get an idea of what's going on. So first of all, I always like to start super basic, and I used this tool a ton as a system administrator because it's really easy to remember, it's really easy to type quickly, and it gives you like a really good snapshot of what's going on right now with memory on your system. And that's just the command free. It's basically you could say what's my free memory at the moment, right? But of course, it's showing you more than just your free memory. It shows you your total, it shows you your swap, it shows you used and your free memory. And of course, it also goes into buffers and cache. Now, older versions of this tool didn't include buffers and cache. You had to kind of like, or it did, but it wasn't as obvious. So you had to like do some math to figure out what you actually had available. It's better now. They've improved it. Also, you might notice these numbers are very large. That's because it's displayed in kilobytes. We can do free dash M to tell it to show me megabytes. I think dash G also works to show you gigabytes, but I like to use free dash H, which is human readable, which basically takes it and puts it in the most logical unit based on the size of the number that it's trying to display. So you can see the total is listed in gigabytes or gibibytes, I guess is what I'm supposed to be saying here, and used is in megabytes or however you pronounce that now, because the number, of course, is in meg instead of in gig. So all right. So that's one good useful tool. Another one that gives you a lot of the same information, but more of it is called vmstat. If you're familiar with the tool iostat, which does this for disks, it does this for memory, right? So VM for virtual memory, stat. And you can see right there, it gives you basically the same kind of information, but it gives you some additional stuff here, right? There's these additional information about swap in and swap out. There's information about IO, memory IO, system, and CPU, right? This is more like load averages and weights and whatnot. And of course, this also has some nice, useful command line options. Telling it to display in meg versus k is 2 characters instead of 1 like it is on free, but it's vm stat dash capital S and then an M says display it in meg. So that makes the numbers a little bit easier to read. There's also a different format you can display it in, vm stat dash S, which gives you like this sort of longer list and a little better descriptions as to what all those little abbreviations mean. So maybe you like this a little better. Maybe it's easier to read. And there's also a way, if you remember, iostat gives you like this point in time snapshot, but it can also do it every couple of seconds. So you can see what's going on with the system. vmstat will let you do that too. So if I do vmstat and then the number 2, which tells it to run every 2 seconds, and then again, another number, which is the number of times it should run, right? So this will run every 2 seconds for 15 instances, 15 runs, right? Now it's going to give us a running tally of what's going on our system. And on this particular system, this isn't going to change much because it's just a lab system and there's nothing going on this machine. So you're not going to see the memory footprint change all that much. You might see little bits as the operating system is doing things in and out. Anything about vmstat you'd like to share, Scott? I know you use this tool a lot more than me. I was always a free person because I'm simple.
Yeah, well, I think where vmstat is really handy is when you've discovered something with free or by running just vmstat on its own and you're looking at that kind of aggregate system data. But you want to know more about what the system's actually doing right now. That's where running it as a series of uh, runs is important because
Right,
when you ran it, you got like the system aggregate first, but then each run after that was basically the window of what had changed in the last 2 seconds. And so,
right.
for example, uh, I've noticed a bunch of people online recently asking about swap. And so it's like you're using swap, okay, but are you really using swap? Like, what did your swap in and swap out look like? So if you're running vmstat over a series, you can actually see, is it actually performing swap operations? Or
Right.
is this is stuff that's like been swapped out over time and it's just kind of in long-term holding out in swap, right? If it's swapping in and out over, significantly in a short period of time, that's concerning. If there's really not swap activity happening, but there's a bunch of stuff there, that's less concerning.
Right. Right. Now you could use free with like the watch command, but now you're chaining two commands and it doesn't give you that tally, right? vmstat gave it to you row by row, where running free gives it to you in one block, and every time you run it, it would overwrite that block. So, handy tool. Good to have several tools to do the same thing depending on what you're looking for. Really, the way, kind of the Linux way, right? Let's give you 28 tools to do the same thing. All of them work slightly differently and might be beneficial in different use cases. Okay, so the next thing I wanted to talk was PS, which of course is how you look at processes that are running on a Linux machine. So just plain old PS gives you what this current user is running, like what's running is this user. PSAUX AUX, not WX, is a very common command. You've probably done this a million times if you're a systems administrator. It shows you all the processes and it gives you some extended information and what users they're running as, right? And there you go. You can see this will show me, because I'm running it as root, it'll show me all of the details about all of the processes that are running on this particular lab system. If you run this as a user, I think it gives you the same list, but it doesn't give you all of the output because you don't have permissions to read some of it, right? So just keep that in mind. A couple columns I wanted to focus on here. There's this RSS column, which is not RSS like, you're pulling in your newsfeed. This is RSS, which is the physical memory that this process is using, right? So there's a chunk of physical memory allocated to this process that takes up this much space, right? And then there's VSZ, also sometimes called VSS, I think, if you look at the man page.
Just 1 second. Nate got disconnected, but he'll be back in a second.
I think I got my sentence out before that happened. So this is the virtual memory footprint. And this is basically, some people synonymize swap and virtual memory. And in this case, it's actually more like this is memory that this process can expand into, right? So when the process starts up, it says, this is my virtual memory footprint, and this is how much I'm actually using. That may end up in swap. It may not end up in swap, right? This particular system, because it's a lab machine, doesn't actually have any swap. So that virtual memory can't be swapped. It's actually a virtual allocation within the block of memory, which could be a problem if we over allocate the system and all the processes try to use that. That's what swap's for.
And Nate, if we have time at the end of the show, I'll actually talk some about how individual process memory is managed. And I think that'll clear up maybe some of the, what does virtual size for a process really mean and how does it look?
Right. Since this is critical path, we're going to move along quickly. I didn't want to go too deep on that. So for the next thing, let me just switch my share here. You don't have to do anything, Scott. Just a moment. All right, so this is actually in my home lab, and the reason I wanted to switch to this machine is because it has a whole lot more going on it, because it's running a bunch of Podman containers, it's running a bunch of VMs, so there's a bunch more things going on in memory, a bunch more processes running. And you'll notice I'm running these as a normal user because this data can be collected as a normal user as well. The first thing I wanted to show you was top. Again, top is, if you're not familiar with top, I don't know what you're doing with your life, because top is like I would say every system administrator's go-to for what the heck is going on right now in my system. And of course, this gives you things like load average. It gives you some statistics on memory, and it gives you this like constantly updated screen, or the constantly updated output that will update. I think it's every second, 22 seconds, something like that. Now, the reason I wanted to do this particular command on this machine is because our lab machines only have one CPU. This one has 12. If you hit the number 1 while looking at top, it'll show you a breakdown of every single CPU, right? And what's running. Now, this isn't necessarily memory related, although some of it is really helpful when you're thinking about performance, because it gives you all these columns about user space and system and disk weight and idle time. Really helpful stuff. But when we're talking about memory, of course, you're going to want to look at these columns down here where it says virtual memory, resident memory, shared memory, things like that. And of course, how much CPU this particular process is taking up. You can see Cockpit is taking up like a whole CPU right now, probably because I'm running this session through Cockpit, right? So Top, really handy tool. Any words of wisdom with Top before I close the screen, Scott?
Srineth notes that your load average is about 4. And just that is not necessarily a bad thing.
Right.
Because things can be.
I'm using CPUs on this machine because it's a multi-core system. The load average is kind of misleading. If you've been in this game long enough that you remember single-threaded or single CPU systems, you would remember a load average of 1 was usually synonymous with a system that is overloaded. It has 100% of one CPU is in use. That's not the way load average translates in a multi-CPU system. And correct me if I'm wrong here, Scott, but this comes down to the number of processes that are waiting for CPU. Is that?
Yeah, it's the average CPU run queue depth.
Run queue depth. So if I have 12 cores, a run queue depth of 12 would mean that all my cores are doing something, right? And of course, that load average goes across time, right? So if it stayed that way, or if it went to like 40 and it stayed there, then that means that there's a ton of things that are waiting for CPU in my system, right? So again, the load average of 2.5 or 2.8 or whatever on my system right now doesn't really indicate a problem. It just means that there's things running on the 12 cores that I've got available to me.
So I disagree slightly with your assessment.
Okay.
If you had 12 cores and all 12 of them were doing something, the run queue would be 0, right? Because they're all running. They're not queued up running, queued up waiting for running. But there's a lot of things that can get something in the CPU run queue. Sorry, let's try that again. That get you in the CPU run queue that are not necessarily a bad thing. When I've seen really huge CPU run queue depths, it's actually pointed to disk I/O problems, not CPU problems. So things like processes will check periodically and will have to be run on the CPU to be checked periodically to see if their I/O requests have been resolved. And so they might hang out in the run queue just cycling through to see if that thing has been resolved, which is how if you have disk problems, all of a sudden you have a really huge CPU run queue depth. So
speaking of disk I/O, that's the reason I like this view that I'm showing right now, where I had expanded it to show all my cores. Sorry, I said 12 cores before. I think there's 16 cores in this machine. But you see the 0.0 WA, and some of them are like 0.3, 0. Whatever. That's the disk weight for that particular core. So the process running on that core, how much time it's spending waiting for disk. Man, we're just having fun. Ay. Okay, so anyway, the point is, if all your CPUs or a number of your CPUs are waiting on disk, that could indicate a disk usage problem, or a disk not usage, but a disk I/O problem. Especially if you got like network attached disks or SAN attached disks or whatever. That could indicate like a network problem or just a disk throughput problem. Okay, the last thing I wanted to show was the command swap on. Right, and this tool does a number of things. For example, if I were adding a new swap disk, I would use swap on to activate it. But if I want to just view the swap usage, just swap, I can do swap on -s, and this will tell me these are the swap disks, the swap devices that I have. The reason I use this machine is because it has a physical disk here for swap, which is usually the way you would do this. And of course, it tells me the size of that swap and how much of it's used. Now, you might notice there's like all of my swap used, but I think we're going to talk about that a little more in the deeper dive. All right, and I think that's it for critical path. Any more comments or questions we need to cover?
No, it looks like there was a little bit more discussion about load average, but that's not what we're here to do today. We're here to talk about memory.
My misremembering of how load average works. Sorry, folks.
Yeah. So don't forget to mash that like and subscribe button. We're going to play the 2-second transition animation. And when we come back from that, we're then going to go into our deeper dive and we're going to answer some questions like, how is virtual memory different than RAM? Do I even need a swap? And if so, what size should it be? And then we're going
And
to
why
talk.
is the answer yes?
Well, it turns out the answer is not always yes, but yeah. All right, so stick with us as we transition to our deeper dive.
All right.
Whew. A little bumpy this morning.
That was a fun run through a bunch of system monitoring and performance tooling, and a number already of disconnects and drops and weird things.
Yeah. You were asking before the show if we needed to notify our software provider, and I think the answer is yes.
I think the answer is yes. Yeah. Why? For clarity, folks, we're not actually disconnecting. The thing we use to do the stream is just turning us off and back on again, which then takes us out of the scene, and it's not helpful.
All right. So, virtual memory versus memory. And Nate, you started to talk some about this in the critical path, but a lot of people use the terms interchangeably, and it turns out that in compute world, they are not interchangeable. So, memory, like RAM, is the physical devices that store memory on a machine, right? So, like the DIMMs or SIMs, if you're really old, that store stuff used by your computer. That's memory. But it was very expensive. And so what we started doing is using disk space to supplement that. And that's what swap is. So swap is a disk device that is used to supplement your memory on your computer. And when you supplement it, that gives you additional capacity, right? So virtual memory is your RAM plus your swap, right? That's your system's total amount of virtual memory.
Right.
Now, in reality, like disk-based storage for stuff is not as good as RAM because it's slower. And you have to do things like get data in and out of the disk IO subsystem. So you have like all the disk IO overhead for getting data in and out of your swap space. So it's preferable for computing to store your data in RAM for your applications because then the computer, the process when it needs it, can readily access it. There's not a lot of time lag between when the request is made and when it's serviced back by your operating system kernel to that application. Whereas if you have a request that is for a piece of data that's on swap, instead of just the operating system kernel retrieving it from memory and passing a memory address to the application, it instead is, okay, we're going to do some disk IO. We're going to swap in our data to memory. And then once we have it swapped into memory, we can provide the memory address to the process that requested it. Right. So all that additional transaction stuff makes swaps slower, significantly slower. That's also why people are always like, don't put things in swap, because if it's something that's used, we know that accessing it takes a lot longer.
Right. Right. Now, obviously, that's a different world now than in days when everything was on spinning disk, right? Because disks are much faster, but there is still overhead to that, which is what Scott was just describing.
Right. Even if you're using SSDs for your swap, it will be less efficient and take
Right.
longer to resolve memory requests than if you use just natively stored in RAM. All right.
Man.
Uh, in the chat of our stream. Oh, by the way, if you're a deferred guest, please please feel free to leave us a comment and we will respond via comments. But those of you who join us live can ask questions in the chat. So JScar asked what our take was on having swap. Like, do you even need it? And I think the answer is largely yes. Having it doesn't hurt things generally. But there are places where you don't use it. For example, cloud instances very rarely have a swap. Though the reason for that is actually a compute and cloud architecture thing, not necessarily a Linux thing, right? So in cloud world, when you add a disk or you allocate some disk to your machine, who knows where that lives? Right? It's out there in some cloud, which might
Mhm.
be in a storage zone or something else. There's also not a lot of like guaranteed consistency in that backing storage. So if we're in a situation where we need to retrieve a piece of data from swap to service a process request, what happens if the cloud storage where your swap is just happens to be extra slow that day? Well, now you're like swap ins from that extra slow disk take even extra more time. And so in the early days of cloud, where things like weird latency and other stuff happened more regularly, they just said no swap for
Right.
machine. And that is kind of a tradition that we carry on today, even though uh, the disk backends for cloud providers have gotten substantially improved over the last 10, 15 years.
So the answer is it depends.
Right. It
Usually
depends.
yes, sometimes no.
Well, that kind of leads into like how is swap used for things, right?
Right. Right.
And I think the other question that kind of falls in there is like, if I was going to have a swap space, how big would I need it to be? And that is also an it depends. So, for example, if you're a laptop user, you probably want a swap that's close to your amount of RAM because swap is used for things like suspend operations for laptops. So we
Mhm.
take like RAM state and we persist it out to the swap space, and that's how we can then like keep the machine cold and not use a bunch of power to maintain the charge in the RAM modules and keep the memories going. Um,
And Andre in chat just said that exact same thing, but they're probably 3 seconds behind us and didn't realize you were saying
right.
it.
Uh, but if you're not a laptop user, or you're a laptop user but you don't really care about suspend operations, maybe you don't need that.
Right.
First, you probably don't need something that's equal to RAM. It's going to be less than that. So, um, so it depends. I think the really key thing is the laptop use case, and if you're not a laptop use case, you get a lot more flexibility in choosing how much swap.
Right.
The other
Right.
thing,
There used to be good rule of thumb like percentages you would follow. If you had this much RAM, you should have this percentage of swap. If you have that much RAM, and it would change based on how much RAM you had. But now a lot of it is workload specific. So a lot of times what you're doing is looking into the workload you're going to run, find out if it has specific work requirements, and then if so, you should follow those. If it doesn't, then of course you're going to want to try to follow that rule of thumb.
yeah, and the other thing to keep in mind is that you can always add swap space. So you can
Right.
add new disk devices. Nate, in your lab, you're using a logical volume managed swap device.
Hmm.
Just like slap more um, volume group space into that thing. Now it's bigger. Or you can add another logical volume on another volume group or additional disks, and now that could be mixed into your swap organization.
Now,
Um,
that does become more of a problem if you're running physical disk on a physical machine. Virtual disks are different, right? You can add in more virtual disks and boom. But yeah, you'd have to do some like file system resizes if you didn't leave free space on the disk if it's a physical volume that you're trying to put that swap on.
yeah. So, or if it's like you're connected to a SAN, you can like ask for some
Oh
extra
yeah,
and
Yeah.
just what a logical volume, right? That's actually one of the early things for swap was that it could be aggregated together into kind of a homogeneous device, just like we do today with logical volumes, where we take all this disparate disk space and we make it a single addressable unit.
Hmm.
Swap kind of the same way. So you can activate multiple swap spaces. They'll be used um, by the kernel. There's actually another parameter on swap spaces called priority that actually tells the kernel which one to prefer over others. So you can mess around with like
Yeah.
how the thing is. And if
Yeah,
you're real,
you could have seen that in the swap on command that I did. I didn't highlight it, but there was the last column said priority, and there was a number there. So that's how you can tell where it goes first and last.
if you're really desperate for more swap space, Nate, what could you do?
If you're really desperate for more swap space. Oh, are we talking about the kludgy thing I was going to do initially? Yeah. You can make a file full of zeros and then you can format that just like you can do with any sort of a virtual disk. Like you might do this for virtual machines, for example. You make this empty file and then you can write the swap file system to the file because Linux will let you do that. However, and then of course you can activate that as swap. However, that's going to perform even worse than just a normal swap on disk, right? Because it not only has disk I/O to think about, it's got file system and maybe even LVM in the middle there to overhead for all those various layers before it gets down to the disk. So it's always quicker if you can put it like direct in the LVM or direct on disk.
Yeah. And so, like, if you're desperate, you could do that. Totally not the preferred or recommended method of doing it. You want
Yeah.
devices that can get that route.
We used to do that to appease our Oracle database administrator when his ridiculously overspec system, Oracle told him, "You need more swap." Well, the disk is already fully allocated. How am I supposed to give you more swap? So we would make him a file and add it to swap. He never
Um,
noticed.
I see some chat, and the participants are like thinking in the right direction. So, regardless of like how much swap and other stuff, like maybe we should talk about what swap is used for. So, because it's part of the virtual memory subsystem, it's used to supplement system memory, right? So there's RAM and swap together as virtual memory. And what happens is the kernel will kind of scan through RAM looking for RAM that it could send a swap space. And it looks for unused things in memory. So it's typically not going to pick something that's active or frequently active, because if it used that thing and sent it out to swap, then it would just have to pull it back in again the next time somebody used it. So it's looking for inactive pages of memory to then swap. Now, Andre mentioned a tunable called vmswappiness. So let me pull up my machine here. And in Proxys VM, these are all the different virtual memory tunables that you have for the kernel. And Andre was talking about this one, swappiness. And so if we just take a look at it, the default for this machine is a swappiness value of 30. Now, swappiness is a value that runs between 0 and 200. Many of you are probably going, wait, I thought it was between 0 and 100. No,
Right.
0 to 200. This is a more recent change to how the kernel manages swap space. And so essentially, what you're setting with swappiness is one, how aggressively the kernel should use swap, and two, what type of thing it should target for swapping. So basically, between 1 and 100, you're telling the kernel that you would prefer it to swap pagecache, which is like cached memory that we use for various other things. Between 100 or 101 and 200, you're telling the kernel you would prefer it to be more aggressive swapping anonymous pages. So both anonymous pages and page cache are candidates for swapping, and the swappiness setting simply tells the kernel which one of those two things you're more interested in having it swap when it's managing the swap space. So at a swap space of 30 or a swappiness of 30, I'm telling it I am more interested in it using pagecache for doing swapping. And I'm also not super aggressive when trying to swap pagecache. And I should not really be super aggressive about swapping anonymous pages.
Okay. So a number over 100 would mean that your priority, your preference is toward the anonymous pages.
Yeah.
And the higher the number, then what? The more aggressive, or the lower the number, the more aggressive? Like, is
So
100 the middle point, and like this way is more aggressive one way, and this way is more aggressive the other way, or is it more like
So essentially, like 100, let's just call it 100. You're saying, I want you to be more aggressively swappy, and I want you to be aggressively swappy around um, around page cache.
okay,
And at 101, we start to tip the other way, and it's like I want you to be aggressively swappy, but I want you to be aggressively swappy on page cache and a little bit on anonymous pages.
okay? And then the closer to 200 you get, the more you lean it toward anonymous.
Correct. So like
But
at
then the
one
closer to 0 you get, the more aggressive you get toward virtual memory. Or
Uh, the closer to 0 you're getting, you're telling it that you want it to be, that you want to be less aggressive when swapping things.
less
So
aggressive towards, okay.
yeah.
All right.
So
Sorry if I'm
if
confusing people. I'm trying to make sure that not only that I better understand it, but that the people viewing get a better understanding of it.
and there's actually a really great article on this written by Chris Down, who works at Meta as a SRE, but he does a lot of kernel stuff. So give me 1 second and I will paste it into our thing here. And he actually gives a kind of formula for when I set it at this versus that, how do I
Hmm,
actually address that for swap space, right? So
okay.
if encryption is not hitting home, there is a formula where you can plug in the numbers and it'll like tell you which one you're being more and less aggressive on. All
There
right.
was a
So if
question about when this was introduced in the kernel. I don't know that we have that information offhand, or even if the article goes into that. Like
it
when the over 100 was introduced in the kernel, or has it always been there?
so the article doesn't go into it. I did not see it. Let's try that again. I did not see it until like RHEL 8-ish. So
Okay.
it's been for a bit. I don't know exactly when it came in. Um, all right. So I changed the swappiness, and because I set it to over 100 now, I'm preferring anonymous pages to page cache when performing swapping. But I'm not super aggressive, right? If it was more like 200, now I'm going to be super aggressive. And so the differential between them is how do we use page cache versus anonymous pages? And why would I like manipulate this in this way? You'll notice that if you look at online guides, almost all of them have you setting swappiness to a value less than 100, and many of them, including things like database workloads and other stuff, have you setting it down to like 10 or 20 as your preferred size. Some will even go further and say you should set it to 1 because they want it to be as least swappy as possible. But what you're really doing is telling it you want it to be as least swappy as possible on anonymous pages, because it turns out that all those workloads allocate memory and then use that memory inside of their process space to do things like their own internal caching. And so by swapping out anonymous pages from applications, you're swapping out application specific data that if the application needs it, now it has to go and swap it back in again, which is a slow process, right? It can hamper your performance of your application. And so when the database and other application vendors are saying, set it really low to like 1, what they're doing is they're saying, if you're going to swap page cache, because we want to keep our anonymous pages in memory so that if we need them, it doesn't cause our application to be slow because we have to wait for a swap in process. So that's what kind of is happening with swappiness. Now,
And
yeah,
William in chat brings up a really good point. There's a tool in RHEL, and I guess any distribution that supports tuned, that will allow you to use tuned profiles to set the swappiness. So you may not have to care about it if there's a tuned profile that already fits your needs. So if you don't want to have to think about it, you could look into tuned profiles as well.
and Billy is like, again, our audience is great today. They're like forward looking. So
Yeah.
our way today at the end of the episode is going to be like, try tuned, because like I just set the swappiness value in memory, which means if I reboot the machine, it'll go back to its default, which was 30. So how do you persist changes? And you can use syscontrol, but a more modern way would be to use tuned. And I'm going to throw people a tuned lab that I think will give them a good introduction and primer to setting permanent tunable changes using the tuned daemon, which is turned on by default in RHEL.
So the real question here, Scott, is, are they predicting where we're going with this because it's logical, or are they predicting where we're going with this because we're predictable?
I mean, yes. All right. So
Let's be less predictable.
So I wanted to cover a couple other virtual memory tunables. I wanted to talk about this one, trap caches. So in the critical path, Nate showed us free,
Oh, right.
right? And part of free is this memory that we're using for buffers and caches. So drop caches will purge this memory, or at least whatever is not actively being used in this memory. And so you can send different values into drop caches to tell it to drop different types of caches. So if I send a 1 into drop caches, it drops slab cache, which is a pre-allocated pile of memory that's a specific size the kernel can just like hand to applications that are asking for memory. So echoing 1 into drop caches will drop the slab cache, which is included in this buffers and cache line. Echoing a 2 into this is going to drop slab cache and page cache. So you start to drop maybe things that we've looked up on disk that we're storing in memory so we don't have to go out and look it up on disk again, or memory that was decommitted, but we haven't yet cleaned it to reuse that memory register. So it's sticking around in page cache. And then 3, if you echo a 3 into your drop caches, you could see that it significantly lowered my amount of cache memory. That actually says drop all caches except for dirty pages. So these are like buffered disk IO writes that haven't been flushed to disk yet. Those will persist, and that's why it didn't go to 0. It also won't flush things like active buffers for stuff like network connections because they're active and they're used. And if we drop them, that would be bad. So it drops all your directory entry, page, and slab cache if you echo a 3 into that. Now, do you want to do this? Probably not, because we kept that stuff in cache for a reason. It typically will make the system operate smoother. And periodically, the kernel, if you're in a low free memory situation where you need some additional memory or you're using a lot of your memory and there's not a lot of free memory, the kernel will automatically start to reduce the amount used for caching to bump up the amount that is freely available for things. And if there is a large memory request that comes in from an application, the kernel will drop some cache memory in order to free up memory to handle this large memory request that came in. And that's why in the current version of free, under free memory, you actually get all of the available for use memory, whereas in old versions of free, it would not include buffers and caches because that
Right.
was being else, right? So it wasn't free. But the reality is, like, we can allocate it back from buffers and caches pretty easily, and now it can be used as free memory. So in the latest versions of free, the free memory also includes that memory that is over there in buffers and caches. And that's actually, you'll see if you look at free and available, the two numbers are pretty close, except for those buffers and caches I wasn't able to get rid of when I dropped them.
Right.
All right. The last memory management thing that I want to go over actually touches on the virtual size that Nate mentioned in the critical path. All right. So remember when Nate was showing us PS, he said, "Oh, look, here's your virtual size and your resident size." All right. So resident size is like how much actual RAM is being, or virtual memory is being used by this application. Actually, I take that back. It's how much real system memory is being used by the application. So it doesn't include anything that's been swapped out. But the V size is the address space allocated to this process. So it's often the case the processes will ask for a pile of memory, but then not immediately use it all. And so what the kernel does is it just kind of like creates a process address space for memory. And it says, oh, you asked for a gig of RAM. Here's an address space with a gig worth of RAM memory addresses in it. And then the application starts putting things in those memory addresses, which then the kernel uses a subroutine to actually map that to system memory. So process memory is always kind of separate and managed by the process, but that's in a separate address space that the kernel allocates to each individual process. And so we can look at that process memory using pmap. Actually, I installed Apache so we could use it to look at its process memory. So if I do a pmap of process 2525, so this is actually telling me the process address space that's being used by this Apache process. And it gives me the starting memory address and the process memory address space, the amount of memory, and what it's being used for, and also like what it can be used for. And so I mentioned earlier about anonymous pages, or like a piece of data used for internal process data storage. And you can see here that this Apache daemon has some anonymous memory used, right? So it's taken some process specific data and shoved it into this section of memory. And then we see this like lib stuff. What, Nate? I know you know what these lib things are.
Yeah. That'd be shared libraries that have been brought in from the system, right?
Yeah.
Yeah.
And the purpose
Which
of a
also
shared,
take up memory.
yes, but does every process need to have their memory taken up with these shared libraries?
No, because they are shared libraries, and the kernel will intelligently allow processes to read the libraries that are in memory if they're already in memory.
But a individual process doesn't know that somebody else has already loaded that shared memory into RAM. So what happens is the shared library gets loaded by someone who requested it, and it gets put into system memory, and it's assigned to
Mhm.
that process's process memory. And then if another process starts up and wants the same shared object library, it will also request it from the kernel, and it will go into the process memory for that process as well. But in system memory, there's really only one copy stored. So when it's asked for by the process, we'll kind of determine where in its memory address space it lives. But there's probably only one copy of this library actually resident in system memory. And so this is another reason why the virtual size for a process and the resident size for a process are often very different. Because maybe it asked for a bunch of shared object libraries that were loaded into system RAM, but other people had already loaded them. And so it doesn't count against this process's resident memory size, right? It counts against somebody else on the system's resident memory size.
Once again, Scott, chat got there before you did.
Ah, dang it. But we can see if I look at another HTTPD process, right? This one has a bunch more anonymous memory, but then it gets down into the same shared object libraries, right? Because two HTTPD daemons need the same shared object libraries for their normal stuff. So that's an example of where like this process gets loaded, but that memory doesn't count against its against its virtual size. And so if I go back to just the process listing, right, notice that some of them, like this guy, he doesn't have a really large amount of resident memory, but these are more consistent, probably because they have that more anonymous pages shoved into their memory address space. But overall, they ask for an address space of it looks like about a gig each, but they're only using about 15 megs of that space. So we told the process, yes, you can have a gig. Sure, here you go. Here's your addresses for a gig of memory. And then as it started to populate it with data, it's really only using 15 megabytes of that space, which brings me to my next virtual memory tunable. Oops. So by default, thanks to this value being 0, our kernel overcommits memory, right? Because if processes all are like, I need a gig, but I'm only going to use 15 meg, then why would we stop accepting memory requests when we know there's this ton of unused system memory? Because even though people asked for it, they're not using it.
Right.
And so overcommit memory set to 0 says I want to overcommit, and it actually uses a kernel algorithm for figuring out, based on the amount of free space that's left and what people are using, how much should I overcommit to. So it's kind of a dynamic heuristic algorithm for determining how much your system can actually overcommit to. So if you actually went through like all the processes on your system and added up their address space sizes, it would be way bigger than the actual virtual memory available on the machine.
Right.
Overcommit. So you can also change your overcommitment policy. You can set this to a 1, which says, I don't want to overcommit. Unless I do, in which case there's a second tunable called overcommit ratio, which is like, I will overcommit up to 25% over my virtual memory, right? So you can set a ratio of how much you're willing to overcommit to. And then you could also set it to 2, which means always overcommit. There is no memory allocation request too large for us to say yes to. We'll always say yes. And that's probably not what you want, because at some point you may need to say no if you've got a lot of things in memory and your system memory is being used.
What could go wrong, Scott? I mean, really, just all the give out memory like free candy.
Exactly. Which is why we default to 0, which is like, use your best estimate and figure out what the machine's doing and kind of like manage it on its own rather than just always saying yes.
Yes, use memory we don't have, but please be careful about it.
Right. So I showed you a new utility called pmap, which is your process map. So it goes through and actually like shows you what the memory address space for a process looks like. And then if we actually went over to proc 2526, what that's actually showing us is like, I think it's this. No, it's one of these others.
Maps, maybe.
Yeah, I think you're right. It's maps. So this is kind of the same thing, right? Except these blanks, those are anon pages. And so it's showing you these are all the memory addresses allocated to the machine and what's stored in them. And this one has a lot of anonymous memory already allocated to it. And then you get down to like the shared object libraries and stuff. So pmap just gives you a more human-friendly way of reading that data. So yeah. So I think that's about it. And we're close to the end of time.
I mean, depends on what time you are referring to. We could be 20 minutes over, or we could be close to the end of time.
Producer Eric doesn't work anymore.
That's true. That's true. We can go as long as we want now. Welcome to In the Terminal, where we take a 30-minute show into 4 hours.
That's right. That's right. So Nate, were there any other questions in chat that I should be aware of?
I didn't see any outright questions that weren't already covered. If there are questions there that you feel like we didn't answer, folks, please feel free to speak up. But it looks like there was a lot of conversation, a lot of people guessing where we were going to go next. But yeah.
All right. So I promised next step of a Tundy lab. So this is the Tundy lab. If you go to the main lab.redhat.com page, it's down under the optimize section. It says optimize performance with Tundy profiles. So that'll give you hands-on for not only making changes like what I was doing, we're talking about tweaking tunables in the kernel, but you can actually make them permanent so that they survive reboots, or you can
Right.
choose Tundy profiles. So like maybe things should be different for a laptop versus a virtual machine versus a like thing that needs a lot of it's a bare metal database system or something. All right. So Nate, do we need a swap?
Mostly yes. Sometimes no.
Yeah. So I mean, you can get away without it, but having one is natural, and the kernel will just like naturally take memory that's not being used a lot out of RAM and put it there.
Right.
So if you didn't have a swap, you'd store all of that memory in RAM that you're not using a lot. And then because it's in RAM, we're not able to do things like uh, swap it out to free up memory for new applications or new address space expansions or whatever for processes, right? So generally, it's pretty good at not messing around with your system. And it's just kind of for long-term storage for things we don't use a lot out of RAM.
Right.
If if you think that you're using swap, you can look at things like vmstat and see what the swap in and swap out amounts are to see if your system is actually doing the churn of like putting things in and out of swap space. And if you are doing that churn of like constantly putting things in and out of swap space, that's telling you that you're in a low memory situation where the reason it's using swap and pulling it back in from swap is because it's not able to take unused things and put them in swap. It's now gotten to the point where it had to take things that are used and put them in swap, which is not healthy and not where you want to be.
Right. That's when you start to see systems slow down. And if you then run out of swap, the kernel starts killing off processes to preserve itself. Right. So if you're out of memory and swap, bad things happen. Don't let that happen.
Yeah, that's when it fires up the out of memory killer kernel
Yeah.
thread, killer, and
Yeah.
it just like picks processes and kills them, thereby freeing their memory. Hey, we solved our memory problem.
Problem
And
solved. Services
yeah,
are down.
which gets into a whole thing of like, how does it choose what to kill? And the answer is like, it doesn't do it really well.
Yeah,
Actually,
I've never. Supposedly it's tunable. I've never really had a lot of luck tuning it that
yeah.
like the important stuff stays up.
So here we can look at our process in process ID directory in proc. There's an score.
Mm-hmm.
So the killer looks at the score of all the processes and it picks the lowest ones and kills those. So if your score is higher, then that protects your process from being killed by killer, at least in the initial rounds, until it's killed off all the things lower and it's now on this one. And then you could do things like uh, score adjust.
There you go.
Didn't work. You can add adjustments to make your number higher or in theory lower. The higher the
In
number, the
theory.
more bit of a service it is.
We used to we had a storage array for like our lower tier stuff that used a user space application to map in its like intelligent storage or whatever, and we'd have systems that were running out of memory, and they would kill off that agent, and all of a sudden the storage would go away. It's like, no, that's the worst thing you could do. Please don't do that.
Yeah, my favorite is SSHD. That's also a really terrible one to kill.
Yeah, don't kill SSHD.
Right.
Bash, anything called bash, don't kill that, please.
These settings are per process ID.
Yeah.
So how do you know what the process ID of SSHD is in advance of having the process start up? So
Right.
if you make adjustments, it has to be part of like a late boot time adjustment script or something. So maybe like
Right.
an article or something along those lines where you can identify those processes, go in and automatically tweak their scores to make them a higher, less likely to be killed score to protect them better. And that way, if it's a boot time process, if you reboot the machine, that'll happen again the next time the system boots. If you just do it like I did, where you just tweak the thing live, that's an in-memory change, and if the machine's rebooted, it's lost.
Right. Right.
All right.
So Shantanu's asking about bumping the priority of critical apps. We kind of just covered that, but I think maybe you just answered that.
I think so.
Yeah, and we're just behind in chat.
Um, but I think that was the end of our prepared remarks today, Nate. Any last takeaways?
Overcommit memory, but do it wisely. Please.
Excellent. So join us next week for another End of the Terminal. We haven't quite figured out what that's going to be yet, but we'll be here to do it.
We'll do something, and we'll probably get it right.
And I know that I missed last week when Nate was out. That's because I got sick earlier in the week and then was like behind all week and couldn't.
I mean, we're both just slackers, right? I was on vacation and you were sick. I don't know why we didn't just get together and do a show anyway.
I mean, good thing you're not the boss, Nate. That'd be deadly. So next week we'll do another End of the Terminal. Just a reminder that RHEL Presents is going to be on pause for a bit. So as many of you know, producer Eric left our team and went to go work for another team at Red Hat. But as part of that, he's no longer hosting and managing RHEL Presents. So we need to find another host before we can have that continue on. So we'll pause it for a bit, and then once we get a new person joining the team, we'll maybe reinvigorate that program a bit.
As fun as it would be, Scott and I can't do nothing but live streams. So.
J Scar was saying that he hopes I feel better, and yes, I'm back to like 100%. So thank you for asking after me, J Scar.
Or at least as close to 100% as you were before you got sick, right?
Exactly. Oh, Ben Ferrer says that next week we'll be doing System D, and he'll be here to do it. Excellent.
Oh, good. There you go. We'll let Ben run into the terminal for a week. It'll be all about System D. I think I still have my shirt. Everybody loves System D from when he was on RHEL Presents.
All right, everyone. Try out the TuneD Lab. Thanks for watching on memory management and like, do you actually need swap? Probably, but maybe not if you're a cloud person.
Maybe you do. You should probably do. Yeah. Well, we'll stick with that. Like 98%, yes.
It adds some resiliency and costs you, right? But there are times where anyway, we've hashed that out. We'll see you next week for TBD, maybe System D if Ben Briard is really committed to the System D thing. And it's always great to see you all. Take care.
Yep. Have a great one, folks.